Gosh, why is this lead so weak? It's so useless.
Actually, that lead is made out of graphite, and that graphite is made out of graphene, which is super useful and super strong.
What the heck is graphene?
Here, let me show you.
Let's first introduce graphite. Graphite is a layered structure consisting of rings of 6 carbon atoms. Graphite crystallizes in a honeycomb pattern. These layers are now held together very tightly, as they are only held together by van der Waals dispersion forces. Because of the weak forces between layers and its crystallization pattern, it is unlike diamond, which is also made up of only carbon atoms. Graphite instead is dark gray to black, opaque, and very soft. The atoms within a layer are held together by strong covalent bonds, stronger in fact than in diamond. This layer is referred to as graphene. Before the discovery of the graphene, a truly flat 2D material was thought to be impossible to obtain. However, in 2004, Audrey and his colleague Konstantin Novislov were able to obtain graphene through the patience and persistence of using a piece of tape and a graphite crystal to thin out the graphite until a single layer was obtained. This new material is thinner than paper, stronger than diamond, and more conductive than copper. Graphene can be extracted from a graphite crystal through a top-down approach or a bottom-up approach. The bottom-up approach involves the self-assembly of graphene from small molecules. Here's a quick demo of the top-down approach, known as the Scotch tape method, but also might be referred to as micromechanical cleavage or mechanical exfoliation. In this process, we take a piece of tape and place it on top of the graphite crystal. Using a cotton swab, we swipe across the tape in one direction to properly space out the graphite material. A side note, depending on the direction of the swiping, the properties of the multi-layer graphene extracted will change. Then this tape is placed down on a surface and another tape is used on top of that one. This process is repeated until we get a very thin layer of graphite, and then we spread out the material within the tape to get an even layer. I didn't show it in the video, but you spread out the final tape by folding it upon itself multiple times. Graphene's applications are endless. They extend to energy industries, medicine, electronics, the food industry, sports, and technology. Although graphene application is vast, integration into these industries face challenges, such as mass production of high-quality graphene, production at a level larger than the nanoscale, and integration into existing technology. That being said, graphene is truly one of the most versatile molecules in the world.
Whoa, that's interesting. Since graphene is derived from graphite, does graphene also have its own derivatives?
Actually, I'm glad you asked.
Although graphene was first isolated in 2004, graphite oxide was actually first synthesized in 1859, when Oxford University chemist Benjamin C. Brodie treated graphite with nitric acid and potassium chlorate, producing an oxidized form of graphite known as graphite acid. He didn't know at the time, but his experiment was the first towards the discovery of graphene oxide. Graphene oxide is a derivative of graphene, sometimes referred to as GO. GO has oxygen-containing groups such as hydroxyl, epoxide, carbonyl, and carboxyl on its surface. These groups make graphene oxide hydrophilic and chemically reactive, useful for functionalization. Because of these oxygen-containing groups, graphene oxide is much easier to disperse in biological environments than pure graphene.
Hey, you. Do you know what graphene is? I bet I know more about graphene than you.
Actually, I do cancer research with graphene, which is a leading molecule in cancer treatment.
Oh, what type of treatment?
Here, let me explain it to you.
Traditional cancer treatments like chemotherapy, radiation, and surgery are effective, but their adverse side effects damage healthy cells along with cancer cells. Graphene-based nanomaterials, especially graphene oxide and reduced graphene oxide, are being studied as advanced platforms for new methods for more targeted cancer therapies. Graphene is currently being explored in multiple treatment types, including chemotherapy, gene therapy, photothermal therapy, photodynamic therapy, and combination therapies that combine multiple treatment strategies. In photothermal therapy, or PTT, graphene materials act as photothermal agents that convert near-infrared light into heat to destroy cancer cells. In photodynamic therapy, or PDT, graphene serves as a carrier for photosensitizers, which generate reactive oxygen species when exposed to light, leading to cancer cell death. Reduced graphene oxide, or RGO, is especially important in these treatments because it has high NIR absorption, high surface area for drug loading, and can be functionalized with targeting molecules to improve tumor selectivity. Because of these properties, graphene-based systems are widely studied for both single-mode therapies like PTT or PDT and dual-mode combination therapies.
Whoa, that's so interesting. What's the mechanism for both therapies, and what role does graphene oxide play in them?
Here, let me show you the mechanism.
In photothermal therapy, RGO absorbs NIR light and converts that energy into heat through photothermal conversion. This localized heating increases the temperature of tumor tissue, causing protein denaturation, DNA damage, cell membrane disruption, and inhibition of angiogenesis, leading to cancer cell death. Since NIR light penetrates tissue effectively, heating can be concentrated at the tumor site while minimizing damage to surrounding healthy tissue. RGO is more effective because it has stronger NIR absorption, making it a more efficient heat generator. The photodynamic therapy mechanism requires three components: light, a photosensitizer, and oxygen. When the photosensitizer is exposed to light, it moves from its ground state to an excited state. It then transfers energy or electrons through two pathways. In a type 1 reaction, electron transfer produces radicals and hydrogen peroxide, which damage cellular membranes. In a type 2 reaction, energy is transferred directly to oxygen, producing singlet oxygen, damaging lipids, proteins, and DNA. GO and RGO enhance PGT by acting as high surface area carriers for photosynthesizers through strong pi-pi stacking interactions, improving drug loading, tumor accumulation, and photostability. When photothermal and photodynamic therapies are combined, the heat from PTT and the reactive oxygen species from PDT work synergistically. This leads to greater tumor shrinkage and improved cancer cell apoptosis compared to the therapies by themselves, overall making graphene oxide a powerful nanomaterial in future cancer treatments.
Can you tell me more about tumor accumulation and targeting?
Actually, I have to head to my lab right now, but I can recommend you this video by my colleague.
One of the main reasons graphene oxide is so promising in cancer therapy is its ability to selectively accumulate in tumor tissues. This targeting occurs through both passive and active mechanisms. Passive targeting relies on something called enhanced permeability and retention effect, or EPR effect. Tumors grow rapidly and form abnormal blood vessels that are poorly organized and highly leaky. These gaps in the vasculature allow nanoparticles like graphene oxide to escape from the bloodstream and enter tumor tissue more easily than they would in healthy tissue. At the same time, tumors have inefficient lymphatic drainage, meaning the nanoparticles that enter tend to remain trapped there. This leads to preferential accumulation within the tumor microenvironment. However, passive targeting alone is not always sufficient, especially in human tumors where the EPR effect can be inconsistent. That's where active targeting becomes important. Graphene oxide naturally contains oxygen-based functional groups that act as chemical attachment points. Scientists use these groups to attach targeting ligands like antibodies, peptides, or folic acids. Cancer cells often have receptors that are overexpressed compared to normal cells. These targeting ligands recognize receptors that are overexpressed on cancer cells. When binding occurs, the nanoparticle is pulled into the cell through receptor-mediated endocytosis, improving tumor specificity. Whoa, that's so interesting. But if graphene is that amazing for cancer therapy, why aren't we seeing it everywhere already? Is there something risky about it? Okay, wait. Let's see if this video talks about it. Despite its promising therapeutic potential, graphene oxide is not yet ready for widespread clinical use due to several safety concerns. One major issue is dose-dependent toxicity. At lower concentrations, graphene oxide may be relatively biocompatible. However, at higher doses, it can induce oxidative stress, disrupt cell membranes, damage mitochondria, and even cause DNA fragmentation. This means that while it can effectively kill cancer cells, it may also harm healthy cells if not carefully controlled. In addition, graphene oxide tends to accumulate in organs such as the liver, spleen, and lungs, raising concerns about long-term retention, and chronic toxicity. Its biodegradation pathways are still not fully understood, making it difficult to predict how the body processes and eliminates it over time. Finally, variability in synthesis methods leads to inconsistencies in particle size and surface chemistry, complicating reproducibility and regulatory approval. These challenges must be addressed before graphene oxide can safely transition from preclinical research to routine clinical practice.
Whoa, that's so interesting. I feel like I learned a lot about something I use every day.
Yeah, your questions were great. I'm glad you asked. I learned some new stuff too.
Okay, let's log back in. Bruh.